Okay, good morning, everyone. Welcome to this week's IQS seminar. We have our own Alok Singh with us today. He'll be talking us about thermoelectric effects in superconductors. How can we get them? Alok, the floor is yours.
Thank you, Vivek. So I'll be talking about how to obtain thermoelectric effects using the particle hole symmetry breaking near Abrikosov vortices in type 2 superconductors. And this is a work I did with Seebeck and our Italian colleagues Ali and France, and of course with Andrew as well. Here is an outline of the things I'm going to be talking today. If this works. Okay. So first I'm going to be discussing the BCS theory. Some of the concepts involved there will be crucial in understanding the later part of the talks. And also we'll see how the BCS theory implies particle hole symmetry, which can be broken by introducing a vortex. And to describe the excitations near a vortex, we will have to study the Bogoliubov-de Gennes equations. And we'll see how to numerically solve it. And I'll show you the results that we get out of it in the form of order parameter and the density of states, where the symmetry breaking will become apparent. And then we'll use this symmetry breaking to obtain some thermoelectric effects. I'll go over the two experimental setups that we propose there and discuss the linear and nonlinear responses that we can get out of it. And finally, I'll talk about some of the practical applications that we can get out of the system. So BCS theory, as many of you may already know, Bardeen, Cooper, and Schrieffer provide the first microscopic theory of superconductivity, which explains almost all of the features of type 1 superconductors. And the novel idea in their approach was the formation of Cooper pairs. So Cooper pairs are a pair of electrons in opposite momentum and spin states, and they get paired up via the lattice interaction of electron. But what happens exactly is when an electron passes through the positive ionic background, it attracts the ions near it, and the ions themselves then form a positive charge cloud, which the other electron can get attracted to, and they form a Cooper pair in this process. And the ground state of the BCS superconductor can be expressed in this manner, where the C daggers are the electron creation operators. And so these two terms explain the creation of Cooper pairs, and VK, the modulus of VK provides a probability of occupation of that particular, the square of the Cooper pair in its ground state. But if we want to study the excitations involved in a superconductor, we need to take a deeper look into the Hamiltonian. And here is the exact Hamiltonian for the system, where the first part is the kinetic terms of the constituent electrons involved in this. And the second term gives you the Cooper pair interaction between Cooper pair of different momentum values, where Vk k dash is the interaction matrix element when expressed in the basis of Cooper pairs. So what BCS did was they applied the mean field approximation to it, and they broke down this 4 operator interaction terms into these two operator terms. And in doing so, they introduce a new parameter known as the order parameter, where it can be expressed as an expectation value of the annihilation of Cooper pair weighted by the potential values between them. And the modulus of the order parameter gives you an idea about the superconducting band gap of the material. And for type 1 superconductors, it's just a constant, doesn't depend on the momentum values. So in the whole bulk of the superconductor, there's just a constant band gap. And if we want to diagonalize this Hamiltonian in order to study the nature of the excitations involved, we use what is known as the Bogoliubov transformation, where these quasi-particle operators are expressed as a coherent superposition of the electron and the holes. And the diagonalized Hamiltonian looks like this. So gammas give you the quasi-particle excitations, and the coefficient here gives you the energy of the individual quasi-particles. So it depends on the band gap and the kinetic part of the quasi-particles. So using this Hamiltonian, it's straightforward to calculate the density of states of the quasi-particles. And this is what you get. First of all, it's an even function in energy. So there's this inherent particle hole symmetry in the system, but it also gives you divergences at the values of E equals to plus or minus delta naught, which is not exact. It's an approximate expression, but still this feature of sharp peak remains even if you do experimental measurements for the density of states. And how people measure it is through differential conductance measurements. So at low temperature, the differential conductance is just proportional to the density of states. And so what they measure exactly is they do STM-tip measurements on different parts of the superconductor, and they measure the current for some potential biases and measure the differential conductance. And this is what it looks like for the case of niobium, a layer of niobium. And as you can see, there is this symmetry between the positive and negative energy side. Or in other words, there is particle hole symmetry in the system. So as I mentioned before, in order to break this, we need to study how the excitations behave near a vortex, which you can get by applying sufficient magnetic field. But before going into that, we can look at how, in what ways we can get thermoelectricity in BCS superconductors itself. So Ginzburg in 1944 predicted thermoelectricity, but he did so for spatially inhomogeneous superconductors. Basically, he studied junctions of different superconductors and involved so different band gap values and different phases in them. And using that, you can get some thermoelectricity in this as well, but it took a while to experimentally verify it. People just recently verified it using superconducting interferometers. And also, apart from type 1 superconductors, there's, even if you include the other kinds like high temperature or ferromagnetic systems, there's not a lot of possibilities to obtain thermoelectricity. There are some recent results with respect to it, but like you can get thermoelectricity in ferromagnetic systems, or you can employ some subtle gap engineering involving bipolar Josephson engines. But all of these methods they involve either complicated arrangement of materials or complicated methods to employ them. But what we do is consider just a single unit of type 2 superconductors. So our system is pretty simple in that sense. And we study the excitations near the vortex, as I mentioned before. So in the presence of magnetic field, what you use to describe this is, are a set of two equations known as the Bogoliubov-de Gennes equation. And so because there is a vortex involved, there is no translation symmetry preserved in the system. So you need to express the operators and the potential as a function of distance. And that's what we do here to study the different terms. So HE here is single particle Hamiltonian. So it's just a free particle Hamiltonian in the presence of magnetic field. UKs and VKs are the quasi-particle amplitudes expressed in the position basis. So these are the coefficient that you get out of Bogoliubov transformation, as we saw before, but these are just expressed in terms of position basis now, where these size are electron annihilation operators for a particular position and spin value. And delta again is the order parameter, which the modulus of which gives you the sense of the superconducting band gap. And when expressed as a function of quasi-particle amplitude, this is how it looks like. In our analysis, we are going to study a single Abrikosov vortex. So there is a cylindrical symmetry in the system if you consider around the vortex core. And because of that, you can express the order parameter in this manner. And how we go about numerically solving is basically we start with an ansatz for the order parameter. And then we use the Bogoliubov-de Gennes equations to calculate UKs and VKs, the quasi-particle amplitudes. And using those UKs and VKs, we can again calculate the next approximation for the order parameter. And we repeat this cycle until we get to a converging result. And we do, after a while, get to a converging result. And this is what it looks like for the order parameter. So here I'm expressing order parameter as a function of distance from the vortex core for different values of temperature relative to the critical temperature of the superconductor. This straight line is the BCS band gap value, which is just a constant over the distance. But for a vortex, it changes. It is a function of distance, and it is especially zero at the vortex core, because at the vortex core, there's like perfect magnetic field penetration, and the core behaves in a way like the normal metal state. And so this is, I'm only plotting the radial part of the order parameter here, but since there is cylindrical symmetry involved, if you plot it in 3D, there's like a potential well form of structure forming here. And it's easy to see that there will be some bound states that exist in that potential well. We can take a look at the global density of states that we get from the numerical solutions we have. So this is, I'm plotting this for the case where Kf psi naught is equals to 8. So Kf psi naught is a dimensionless parameter which characterizes the superconductor for our purposes, where Kf is the Fermi wave number and psi naught is the coherence length of the superconductor. And the temperature we take in this is equals to 0.05 times the superconducting transition temperature. So from far away, it looks like the density of states that you get for the type 1 superconductor. The dominant peaks look exactly particle hole symmetric. But if you look closely at the subgap excitations, there are presence of vortex bound states. And if we zoom in on it, you can see that for the positive energy side, the peaks are more dominant compared to the negative energy side. So this is what we refer to as the particle hole symmetry breaking. But a natural question arises at this point that why are we getting a symmetry breaking in the favor of particles? Why are the positive energy peaks are more dominant? To answer that, we have to look at the BDG equation again, and in particular, the single particle Hamiltonian that we use for this. So this is the form of the single particle Hamiltonian that we use, and it inherently assumes that the charge carriers that you have in your system are particle-like. If you use this expression, which then assumes that the charge carriers are hole-like, which you can achieve in p-doped superconductors in specific, you would get symmetry breaking in the favor of holes. So these peaks will be in the opposite manner, basically. We can also take a look at the local density of states to see in more details how these excitations look like. So I'm plotting here the local density of states for two values of Kf psi naught, 1 and 8. And so on the z-axis, there is the local density of states expressed as a function of distance from the vortex and the energy. And I'm only showing the subgap excitations here. So only the subgap energy regime. And as you can see, the positive peak is again very dominant over the negative energy peak, especially at the vortex core where the positive peak has a maximum and the negative energy solution is just 0. So, and for the case of Kf psi naught equals to 8, we see more bound state present inside the subgap regime, but the relative asymmetry is reduced in this case. But on the other hand, the density of states values are higher. So both of these cases have their benefits and drawbacks. Now, since we understand more how the symmetry breaking happens, we can take a look into how we can apply it to the to get some thermoelectric effects out of it. But before going to the results, I would like to discuss what is known as the Seebeck effect. So Seebeck effect is part of two characteristic thermoelectric phenomena, Seebeck and Peltier effect. And in the case of Seebeck effect, what you have is a thermal bias across a material. So we have a hot source and a cold source here. And what N means is that this material has electron-like charge carriers, and you have another material which has hole-like charge carriers. Now, since there is a thermal bias applied here, and since electrons are the particles that enable the thermal current across a material, there will be, the electrons will move toward the colder side. So this side will be left positive in charge as a result, and this side will get negatively charged. And the opposite will happen in the p-doped or the p-type material, where this side will be left negatively charged and this side will be positively charged. So, and you can measure this, these junctions and you can measure that there is a buildup of potential across it, basically. So that is one way to get electricity is just because of the particle nature of the charge carriers involved. But you can enhance this thermoelectric effect even more if you have inherent asymmetry involved in your system. So let's suppose you have a superconductor tunnel coupled to a normal metal here, and the superconductor has a asymmetric density of state structure. And also let's assume that the superconductor is at temperature T and there is a thermal bias where the normal metal is at a higher temperature. So there will be, for the positive energy, or the energy is higher than the Fermi energy of this system, the electron will dominantly tunnel into the superconductor. But on the negative energy side, also the hole will predominantly tunnel into the superconductor as well. But since the density of state structure is asymmetric, the superconductor as a result will acquire a higher negative charge, and the normal metal will acquire a positive charge as a result. So there will be a buildup of potential across this junction just because of the asymmetry involved. And before going to the results, I would also like to say a few words about the linear response, what we exactly mean by it. So to study the thermoelectric phenomenon, you basically have two kind of thermodynamic forces, the potential bias and the temperature biases. And you can get two kinds of responses out of the system, the electrical current or the thermal current. And if the forces are small enough, you can express these responses as a function of the thermodynamic forces in this manner, where this is the Onsager matrix, which can be calculated by this expression. You just need the density of states basically to evaluate it. And using this, you can calculate the basic thermoelectric coefficients, like the Seebeck coefficient, which gives you the extent of thermoelectricity basically. So it gives you the potential bias divided by the thermal bias that you apply, given that the current across the junction is 0, can be expressed as in terms of these Onsager matrix elements. And similarly, the electrical conductivity and thermal conductivity can also be expressed in the Onsager matrix elements. And if you construct a heat engine from this junction, basically, the efficiency that you can get out of this, the maximum efficiency that you can get is expressed in this manner, where eta C is the Carnot efficiency, and ZT is a dimensionless parameter known as figure of matter, and it can be expressed in these other thermoelectric coefficient in this manner, basically. So if ZT is 0, the efficiency that you get is just 0, and if it's large, you approach the Carnot efficiency. We propose two experimental setups to get the thermoelectric effects. The first is an SIN junction, where the interface area is big enough that you consider the whole extent of the vortex. And in this manner, you can get higher values of electric and thermal current across the junction. So for linear response, this is the result that we get, the Seebeck coefficient and the figure of merit. So there are a few things I would like to note here. The Seebeck coefficient for low temperature, specifically T equals to 0.01 TC, the value is relatively high for Kf xi naught equals to 1 case. It approaches a value of 4 millivolts per Kelvin. And also there is a sharp decline in S with increasing temperature, which we'll see later on can be useful in one of the applications that we propose. And also the figure of merit, which again determines the efficiency of the heat engine, reaches a value of 0.5 for Kf xi naught equals to 1, which is in itself a decent value, but as we'll see later, we can do better than this. And for the nonlinear response, in which the thermodynamic forces are large enough, so we cannot apply the linear response regime. Here I'm plotting the thermovoltage, which is just the voltage bias that you need to apply across the junction if you have a large enough thermal bias across it, in order to ensure that the current across the junction is 0. So this is what we get for the thermovoltage. It increases at a faster pace for lower temperature, but at some point it has to saturate. And the superconductor is kept at a lower temperature here, 0.05 TC, and the normal metal is at a higher temperature with respect to it, and goes to a relatively high temperature, like more than 2 times TC. But for those temperature values, it saturates. But I would just like to note that this thermovoltage is expressed relative to the critical temperature. So if you have materials with high critical temperature, the thermovoltage you can get across the junction can be relatively high. And also this is just a response of a single fluxon. If you have multiple fluxons, it should scale up similarly. And for the IV characteristic, this is what it looks like. So what I'm plotting here is just current as a function of voltage bias across the junction for no thermal bias involved here. And if you look at it from far away, it looks pretty symmetric. Like these current values, they look perfectly reciprocal. But again, we have to zoom in on the subcap states contribution. And when you do that for low potential biases, the current looks like this. It is a much smaller value compared to these values that the BCS condensate contributes to, but it is pretty asymmetric, or it shows non-reciprocal behavior. And to characterize this, we plot the rectification factor. It just measures like how asymmetric your current is with respect to positive and negative biases, voltage biases. And for low voltages, it reaches a value of 0.5. But even for a significant range of voltage bias applied, it still holds a value of more than 0.2 for the case of Kf xi naught equals to 4. And also we see again that the asymmetry is more pronounced for the case of lower Kf xi naught. So we can talk about the next experimental setup that we propose. So this is an STM junction where we focus the STM-tip on the core of the vortex. And the idea is basically that the vortex core is the most asymmetric part of the vortex, as we saw in the local density of states plot. So we expect higher values of figure of merit efficiency, basically, if we do that. Again, this is the local density of states plot where we are selectively localizing around the vortex core. And I'm comparing the Seebeck coefficient that we get out of the SIN junction with the STM junction. And you can see it's higher in all of the cases of Kf xi naught, but then it's especially higher for the case of Kf xi naught equals to 8, where there's at least a increase of 6 volts for at least the low temperature values. But the major improvement we see is in the figure of merit. We saw before that V reaches at best a 0.5 value for the figure of merit, but when we selectively localize around the vortex core, we see a relatively high values of figure of merit above 3 for a significant range of voltage. For the case of for a significant range of temperature values. for the case of Kf xi naught equals to 1 and 2. And I'd just like to quote a statement from this review article on the quantum thermoelectric devices, that in spite of recent achievements, the most efficient actual devices still operate at CT around 1. And this is a major improvement over that. But I would just like to caution that this is a theoretical result. In practice, it might be lower, but still it is worthwhile to look into it. We also plot one nonlinear response. So what I'm doing here is using the STM-tip, I'm measuring the current for some the electrical current for some thermal bias applied between the STM-tip and the superconductor. So the superconductor is kept at a temperature of 0.01 times the critical temperature. The STM-tip the tip is relatively small compared to the coherence length of the superconductor. It's like 10 times smaller, and it has a much higher temperature with respect to it as well. And so doing so gives you a sort of an image of the vortex for the vortex core, where the particle-like solutions dominate. You get positive current values. But also in some region around the vortex, you also have negative the whole like contribution that dominate, and it will give you the negative current values. And these are some applications that we propose. So first of all, we can do temperature measurements using the form of Seebeck coefficient that we get. The idea basically is that the Seebeck coefficient is like really sensitive to temperature, especially for the low temperature values. And let's say we have a small thermal bias applied across the junction. The voltage bias that we get across it will be for 0.01 TC will be 2 times what we get for the case of 0.02 TC. For just a small temperature difference, we get a really big difference in the voltage bias. So you can get a sense of what temperatures your material is at based on that. This is another interesting application that we can get out of this. So it's a vortex camera. The idea here is that for let's consider a single vortex. For first of all, for if there is a vortex and there is a single photon that excites it, you can measure the response of it in the form of a voltage bias generated across the junction. So, and if you have a bunch of fluxons in a relatively symmetric pattern, which you can get if you have an Abrikosov lattice. So if there is a high enough magnetic field applied across the superconductor, the vortices form a lattice sort of structure where you can identify the location of each vortices. And as I told you, you can measure the response of single photons impinging on it. So in a way, each of these vortices can act as a pixel in a camera, and you can get an image of the photonic field sort of that you have. And the other application could be as a diode, where we saw the IV characteristic is pretty asymmetric for the low lying voltages, the subgap excitations. And yeah, you can use that asymmetry to potentially build diodes as well. So here's a brief summary of the things I talked about today. We saw that Abrikosov vortices formation in type 2 superconductors can lead to particle pole symmetry breaking, especially the vortex cores, which was also observed in the density of state structure of it. Then we talked about 2 experimental setups that we proposed. One first is an SIN junction, where we observe relatively high values of Seebeck coefficient at low temperature, along with high rectification factor in the IV characteristic, which can be useful for building diodes, as I mentioned. And another experimental setup is the STM junction, where we find even higher values of the linear response coefficient, the Seebeck coefficient, and the figure of merit. And finally, I talked about some applications in the form of a sensitive low temperature thermocouple, a bolometer, or a vortex camera, basically. and a diode. And the paper is out on archive. So if you're interested, you can take a deeper look at it. And that's it from my side.
Questions?
Silly question. You say this leads to particle hole symmetry breaking, but if I understood you correctly, this comes from whether it's a p-doped or an n-doped material?
Yeah.
So isn't the material already have that symmetry broken?
So even metals have that asymmetry. Like for most of the metals, the charge carriers are inherently particle-like because electrons are the dominant charge carriers. But you still, the density of state structure is still symmetric. Yeah, you don't get like, unless you have explicit symmetry breaking. And here, the topology of the vortex creates sort of the thing that breaks the symmetry.
Magnetic field is important.
Right. So you're basically translating this existing
Yeah.
asymmetry into now the density of states because of this magnetic field
Yeah, exactly.
and the vortices. Interesting.
You talked about different Hamiltonian for the holes in one of your earlier slides. So would that be if you started with some kind of different why is it that that one's not appearing in your equation? What's the reason that you have the particle one and not the whole Hamiltonian?
So most of the superconductors are particle-like. The charge carriers are usually particle-like, so that's what we supposed in the Hamiltonian.
Are there even any models of ones that are with the holes? There are.
Yeah, they like some. I know some high temperature superconductors like YBCO and stuff are hold. They are hole doped in specific, so the charge carriers are hole.
I see. And so you get like whole couple pairs of holes, all the same kind of structure.
Yeah.
Okay. Interesting.
Yeah, just symmetry breaking in the opposite manner. Any other questions?
Any questions on Zoom? Okay, if no further questions, let's thank Alok again.